So this video is going to cover the basics of the PV loop. The PV loop looks at pressures and volumes of the left ventricle at various time points in the cardiac cycle. And the reason we care about it is because it gives clinicians a picture of how the heart is functioning. So if we look at the PV loop, we're measuring left ventricular volume on the x-axis and left ventricular pressure on the y-axis. And we're going to take a few minutes here to kind of go through the loop and talk about which phases of the cardiac cycle do we see in each of the different sections. So I like to start with the left ventricular filling phase, which is this phase right here. So the left ventricle is filling at this time. And when we look at the filling phase, we see that we have very low pressures, right? So we're at low pressures of about, 10 or less. And over this time, you can see that there is an increase in the amount of volume in the left ventricle because it's filling. We can break left ventricular filling down even further into rapid filling, which happens first. This is when blood passively moves from the atria into the ventricle. This is followed by a period of reduced filling where there's still blood moving into the ventricle, but it happens, there's a little bit less than the rapid filling phase. And at the very end is our atrial contraction phase, where the atria contract and they add just the last little bit of blood into the ventricles before the ventricles start to contract. So when the ventricle starts contracting, this means that the pressure in the ventricle starts to increase. And when the pressure in the left ventricle is greater than the pressure in the left atrium, that's when the AV valves close. So in this case, we're talking specifically about the mitral valve because we're talking about the left side of the heart, but both AV valves close at that same time. So when we have this increase in pressure, for a while, the left ventricular pressure increases, but it cannot eject blood yet. So we have this period of time here where we have an increase in left ventricular pressure and no change in volume. This is called our isovolumetric contraction phase. So increase in left ventricular pressure, no change in volume because our AV valves are closed. And at this point, our semilunar valves or our aortic valve is also closed. Now, after the ventricle increases in pressure more and more and more, eventually it is going to come to the point where the pressure in the left ventricle becomes higher than the pressure in the aorta. And this is going to open the aortic or the semilunar valves. Once these valves open, then blood can now leave the ventricle and go into the aorta. And as the blood leaves the ventricle, we see that there is a decrease in the volume in the left ventricle, but the pressure in the ventricle is still increasing because the ventricle is still contracting. So this period of time here, this phase, is known as the rapid ejection phase, where blood's leaving the ventricle, lots of blood's leaving the ventricle, the pressure is still increasing. So during this next section, we have a decrease in the pressure in the left ventricle and also a decrease in the volume because we're losing more and more volume into the aorta. This is called our period of reduced ejection. So then the ventricle starts to relax, and as it does that, the pressure in the left ventricle becomes less than the pressure in the aorta. And at that point, that is when we see the closing of the aortic or the semilunar valves. Then we enter a time where the left ventricular pressure is decreasing, but there is no change in volume. This phase we call isovolumetric relaxation. So there's no blood moving out out of the ventricle or into the ventricle because the aortic valve is closed, but the AV valve has not yet opened. So finally, we reach a point when the pressure in the left ventricle becomes less than the pressure in the left atria, and this is going to cause the AV valves to open, and then we can start with filling all over again. So I want you to notice one more thing here, in that we have the PV loop broken down into red and green lines. These lines represent either diastole or systole. So when we think of the phase of the cardiac cycle, the heart is either relaxing or contracting. Those are really the only two options. So when the ventricle is relaxing, we call that diastole. And the two phases of the cardiac cycle that are part of diastole are isovolumetric relaxation and left ventricular filling. So the ventricle is relaxed at both of those two time points. The points when the heart is contracting is known as systole, and systole includes isovolumetric contraction, rapid ejection, and also reduced ejection. Now there are a couple different other points of the PV loop that we should be aware of. There are 3 different volumes that are important to know. The first volume is known as end diastolic volume, or EDV. This is the amount of volume that's in the ventricle at the end of diastole. So the ventricle has been relaxed, it's been filling this whole time. Now at the end of the filling phase, how much volume is in the ventricle? Another point that we need to be aware of is this point here, known as end systolic volume, or ESV. This is the volume in the ventricle at the end of systole. So after the ventricle has squeezed a bunch of blood into the aorta, how much blood is left in the ventricle at the end of systole? There always is some amount of blood left at the end of systole. So that's our ESV. The last volume is the volume that tells us how much blood has been ejected from the heart. So if we take the amount of blood that we started with at the end of diastole, and we subtract the amount of blood that we're left with at the end of systole, we get what's called stroke volume, or SV. So stroke volume is the difference between end diastolic volume and end systolic volume, and we find that by looking at the width of this PV loop. So wider PV loops will have larger stroke volumes, narrower PV loops will have lower stroke volumes. You can also calculate it by looking at what the end diastolic and end systolic volumes are as well. And the last 2 things we need to look at are pressures that we can identify on the PV loop. So systolic blood pressure is this point here. So systolic blood pressure is the maximum blood pressure in the aorta during systole. And if you looked at a Wigger's diagram, you would see that it would correspond with this point right here, systolic blood pressure. And diastolic blood pressure is the minimum or the lowest blood pressure in the aorta during diastole. So right before the semilunar valves open, what is the blood pressure in the aorta? All right, and that's our PV loop.